Good morning, everybody. Or I should say just hello. Might not be morning for you right now. What we're going to talk about today is the second half of Chapter 3.5, and we're really just going to go over some more types of models and their applications. Specifically, we're going to talk about Gaussian, logistic growth, and logarithmic models, and we're going to go through some examples of how to apply those models. The first one we're going to start with is Gaussian, and Gaussian is spelled like this: G-A-U-S-S-I-A-N. And Gaussian is good for normally distributed data. Normally distributed data. Oh my goodness. D-A-T-A. There we go. Normally distributed is a term that you will get more familiar with the further you get into statistics. But basically what it means is this: normally distributed data makes a graph that looks like a bell. We call it the bell curve. And it kind of goes up, curves like a bell, and comes back down. And what's special about normally distributed data is that when it makes this curve, there are two things you can tell about this curve. You can tell that its maximum y value, you can say maximum y value, is the average value of the population. The average value for the population, whatever your population might be. Typically, you are dealing with, well, no, I shouldn't say typically, I should say that commonly, common problems that are normally distributed are things like test scores, and we're going to go over one of those examples. And you should know also that the corresponding x value here with our max value is going to be the average value of the independent variable. So we can just say corresponding x is the average value of the independent variable. Okay. So we're going to use this general knowledge to help us with our problem. Alrighty. So I've got this word problem written down already. If you'd like to pause the video and get all this down, that would be a good idea. I'll just read through it really quickly. In 2001, the Scholastic Aptitude Test, SAT, math scores for college-bound seniors roughly followed a normal distribution. And here we have the model, where X is the SAT score for mathematics. And we're going to sketch the graph of this function. From the graph, estimate the average SAT score. So, one more thing I should add in here that I didn't do earlier before we get started with this problem, just kind of make like a little side note over here. The reason that we're using the Gaussian model here to help us is because this is what the classic Gaussian model looks like, and I should have said that earlier, and I'm sorry. Y equals A times E to the negative outside X minus B squared all over C. And that is the Gaussian model. Okay, so let's get into this problem. Let me keep reading this. Alright, so here is our model. You can see it follows pretty closely here. And we're looking from when the scores were 200 to 800, where X is the SAT score for mathematics. So the scores being from 200 to 800. And we want to sketch the graph of this function. And then from the graph, we want to estimate the average SAT score. So here's what we'll do. If you throw this into your grapher, you will be able to see that normal distribution curve. I'm just going to do a quick sketch by hand. Alrighty, so call this 1. Oh, pardon me. 0.001, 0.002, and 0.003. And up here we'd have half of that. Okay. And we're going to do a little break in our x values because we're really interested from 200 to 800. So I'm not going to start at 1 and go to 200. That would be kind of silly. I'm going to do that little break. It looks like this, kind of like a little lightning bolt type thing. And then I'm going to start my values at 200. And we'll just count by hundreds. 600. Okay. 800. Awesome. So here's what my graph is kind of going to be doing. Our max value for our y, just kind of create this so I don't give you an inaccurate curve here. We're going to begin at the x value, 200, so we'll do a closed circle there because we're not starting before that. And then we kind of make that nice little bell shape up to our max value. And then we come back down, and again we're stopping at the 800 because it's the end of our interval for x. Okay. So if you were to graph this in your grapher and then calculate the maximum value, you would be able to see that the corresponding x value occurs right here when x equals 514. So what we would say then is that the average mathematics score was 514 for college-bound seniors in 2001. So that's pretty interesting. All right. Let's now talk about the next type of model. Let's talk about logistic growth models. Oops, pardon me. Alrighty. And logistic growth models typically follow this formula where we have A all over our 1 plus B times E to the negative Rx. Okay. And what we're interested in now with these types, oh wait, hang on, let me label this for you. So y would be the population size and x is the time. So I can say this is the population size, and we can say x is the time. Okay. And here's what happens with logistic growth models typically. They're dealing with populations that increase at first and then start to decrease. So an example might be bacteria that's allowed to grow under ideal conditions and then under less favorable conditions. We can also call this a sigmoidal curve, but I don't think we're going to refer to that again. A good general graph of logistic growth models looks like this, where you are curving up, increasing to a point, and then after that point in time, you start to taper off and decrease. Okay. And just to highlight for you what is going on there, we call this the increasing rate of growth. And once it meets that point and then it starts to taper off, that is our decreasing rate of growth. Okay. Increasing rate of growth, decreasing rate of growth. Okay. And so, what we're going to talk about now is another word problem. Again, I wrote this one down already just to kind of save some time. If you want to pause the video, write it all down, that would be a good idea. But I'll read through it for you right now. So, on a college campus of 5,000 students, one student returns from vacation with a contagious flu virus. The spread of the virus is modeled by this equation right here, where y is the total number of students. Remember we talked about how y is the population infected after t days, where the variable is time. Okay. The college will cancel classes when 40% or more of the students are sick. And we're asked to answer the two questions. How many students are infected after 5 days? After how many days will the college cancel classes? Okay, so to tackle part A here, after 5 days, well, they give us a value for a variable. They give us a value for time. So you guessed it, we're going to take that value, we're going to substitute it into our model. So for part A, we can say that y equals 5,000 over 1 plus 4,999e to the negative 0.8 times 5. And once we go from here, you can just throw this into your calculator, and when we do that, we should get around 54. So we can say that the number of infected students after 5 days is 54. And remember, you would be rounding up in this case, rounding up or down, because you can't have a fraction of a student. That doesn't make sense. So you have to use a whole number here in your answer. For part B, let's just get a separate sheet of paper going. For part B, we want to know when classes will be canceled, right? Well, they gave us some important information. They said classes will be canceled. Classes will be canceled when 40%, that's important, 40% of students are sick. Well, we can turn this into an actual number that we can use by taking 40% of the population. The population of students is 5,000, right? The college campus had 5,000 students. So what we can do is we can say 5,000 times 0.4, and that gives us the number 2,000. Okay, so 2,000 represents when 40% of the population would be sick. So what we can do is we can solve an exponential equation if we use 2,000 as our y value. So we're going to set up that same model, but instead of writing y, we're now going to write 2,000. We're interested in when 2,000 students are sick. Again, everything else is the same, but we just don't know what our t value is yet, so we're going to find that out. 4,999 e to the negative 0.8 t. All right, there we go. And here is what we can do. We can sort of flip both of these fractions so that we aren't dealing with our variable on the bottom. And so we get 1 over 2,000 equals 1 plus 499e to the negative 0.8t all over 5,000. Now, if we multiply both sides by 5,000, we get 5,000 over 2,000. And then we get 1 plus 4999e to the negative 0.8t. Oh, pardon me, that was at an angle. My mistake. And now what we can do is we can subtract this 1, and we can simplify this fraction. This fraction would just become 2.5, and then we want to subtract 1, and we get 4,999e to the negative 0.8t. When we do the subtraction, we get 1.5, and then we want to also divide away the 4,999. So I get 1.5 divided by 4,999, and I get that that's equal to e to the negative 0.8t. Now, as we've gone through those exponential equations, we should see that now we're able to use a property to help us solve this. When we have an e that we don't want, remember we make everything a natural log. So that's what we're going to do right now. We're going to take the natural log of this fraction. We're going to take the natural log of this e. Remember, when we take the natural log of e, the e goes away. And so what I'm left with is negative 0.8t equals 1.5 over 4,999. And if I divide by negative 0.8t, I will get 1.5 over 4,999 times negative 0.8. Remember that when you divide by something, you actually multiply by its reciprocal. So dividing by that, I put the 1 on top, and so it's now on the bottom of my fraction. And now, when I put all of that in my calculator, what I get, oh my goodness, I forgot something. My goodness. Whoops. This is natural log here. I had to take the natural log of that. I forgot it was over here in blue. So I should say natural log again. Okay. Natural log, and then when I divide by the negative 0.8t, I actually multiply all of this by 1 over 0.8 negative. Now this is accurate. When I put all of this into my calculator, I get approximately 10.1. And so I can use that information, and I can say that after 10 days, at least 40% of students will be sick and classes will be canceled. All right. We've got one more model type to talk about, and that is logarithmic. So, logarithmic models. Alrighty. And remember that the basic logarithmic model looks like, excuse me, y equals a plus b. natural log x, and y equals a plus b log base 10 x. Okay. And remember that their graphs generally do this. Okay. Let's call this 2, 1, 1, 1, and 2. Alrighty, and we come up and we start to curve, and this is a natural log graph with log base 10. We've got sort of the same scale. Oh, that's a negative one. Sort of the same scale going on. But it just looks a little bit different. Okay. Alrighty. And this is when we are using 1 for A and for B. So this is when y equals 1 plus natural log x, and this is when y equals 1 plus log x. Okay. So what we're going to do is we're going to jump right into an application of this type of model. Alright. Again, if you need to take a second to pause the video to write this down, please do so. Alright, so on the Richter scale, the magnitude R of an earthquake of intensity I is this model. R equals log I over I naught, where I naught, and I'm calling this little sub-zero naught because that is what that little zero at the bottom is typically referred to, and it's usually used as like the beginning of something, where something started. Where I naught is 1, that's the minimum intensity used for comparison. So find the intensities per unit of area for the following earthquakes. Tokyo and Yokohama, Japan in 1923, where their scale was 8.3, their intensity was 8.3, and El Salvador in 2001 with an intensity of 7.7. So let's start with the Japan earthquakes. Okay. For part A, we're given I naught is 1, and R is 8.3. So what we can do with this information is use our model to help us. We can put both of these where they go in the model. So instead of writing R for the model, I'm going to fill in 8.3. And I still have log. And I still have I on top, because I don't know what that is, but I do know that I naught on the bottom is 1. And what I can do from here is use my properties, my one-to-one properties of logarithms, where if I have a log with a base, I can put everything as a power of that base and cancel out the logarithm. Since this is regular log, its base is 10, so I'm going to make everything a power of 10. I'm going to do 10 to the 8.3 equals 10 to the log I over 1. And my 10 and my log, pardon me, I never see this as diagonal. Okay. My 10 and my log will cancel each other out, and so I get 10 to the 8.3 equals I over 1. And what I get there is actually I by itself. Remember, anything over 1 is just itself, so I've really already solved for I. And what you can kind of do is just sort of cross out that 1. And when I put 10 to the 8.3 in my calculator, I get that I is approximately 199,526,000. Okay. To do part B, we're going to do a very similar process, except in this case, oh, pardon me, I naught is still 1, but R isn't 8.3, it's 7.7. So I'm going to use that information into the model that they gave me. I'm going to say 7.7 equals log, and then I'm going to say I over 1, or really, since we know what happened last time, we can just say I. And what we can do this time once more is the same process, because my base number is still 10, so I'm going to make everything a power of 10. 10 to the 7.7 equals 10 to the log I. When my 10 and my log go away, I get that I is equal to 10 to the 7.7. When I use my calculator to help me, I see that I is approximately 50,119,000. Okay. Alrighty, so what we can do with this information is, we can take the first intensity and divide by the second intensity. And when we do that, we can understand just how much more intense the Japan earthquake was than the El Salvador earthquake. So, we did already find the two intensities. We answered the question, but let's take it just one step further. If we take the first Japan intensity over the El Salvador intensity, we see that we get approximately 4. And what this is saying is that the Japan earthquake is approximately 4 times more intense than the El Salvador earthquake. And that's a pretty big jump, because it looks like our values weren't that different. It was only a difference of 0.6, but that is actually pretty significant with the Richter scale. Alrighty, thank you for watching. We'll see you in class tomorrow.